Okay, in this lesson we're going to discuss flux and EMF graphs. In other words, I'm going to show you how we can graph the flux through a coil as the coil spins in a magnetic field, and how we can use that graph of the flux to determine what the graph of the EMF looks like. So let's start. Now, what we have here are we have 5 diagrams of a coil, the same coil spinning in a magnetic field. So in this first diagram, we've got we'll label the normal to the coil, and that normal is pointing upwards. So I'm drawing the normal in blue. So initially the coil, the normal of the coil is facing upwards. Now this coil is spinning in a clockwise direction. So some very small time later, the coil is now oriented like this. And then like this, and then like that, and then finally it returns to its original position. So it's done a complete 360 rotation. As I'm sure you are aware, the green lines represent the magnetic field. So the blue line is the normal to the coil, and the green line, the green vectors, are the magnetic field. So what we want to do, we want to see how we can use what the flux is doing through the coil to look at what the EMF is doing in the coil. In other words, get a picture of what the voltage looks like in the coil. So what we're going to do, we're going to construct a graph. Actually, we're going to construct 3 graphs, and I'll show you why. So we'll just draw 1, 2, 3 sets of vertical axes. And 1, 2, and 3 sets of horizontal axes. Okay, so before we look at these graphs, let me explain what these graphs are and where they're coming from. All of this is coming from Faradays Law. Now, if you remember, Faradays Law, the EMF generated in a coil or in a conductor is related to the negative rate of change of the flux over time. So it's not related to the flux through the coil, it's related to the rate of change of flux through the coil. Now this rate idea, the rate of change, that's the gradient of the flux graph. In other words, this section here, these delta signs are telling us that the EMF is related to the gradient of the flux time graph. And to be even more specific, the EMF is equal to the negative of the gradient of the flux time graph. So that means if we were to plot or create a flux versus time graph, and then plot the change in flux, the change in flux versus time, then we will finally be able to get the EMF versus time. So we're going to start with the flux graph and we're going to get to the EMF graph. So we're actually going to see what the EMF is doing as this coil spins in the magnetic field. So let's have a look. So in this first situation, in scene A, the coil, the normal to the coil, is at right angles to the magnetic field. And that means that the angle between N and B is 90 degrees. And if we use our formula that the flux is equal to BA cos theta, that means that the cos of 90 is 0, so the flux will be 0. And it's fairly obvious in this diagram too that the field lines aren't threading through the coil. So in this first position, and we'll make our time start right on the axis here, so the flux through the coil is 0. That's corresponding to position A. In position B, we can see now that the coil is rotated 90 degrees in the clockwise direction. So now we've got the maximum amount of flux passing through the coil. So in this position, we're going to have the maximum flux. So it's going to be some value up there. And that's our position B. As the coil spins again, it's spun around to this position. Once again, the angle is 90 degrees, and so the flux is going to be 0. So the flux comes back to 0. Now, in this, that's position C, and here's position D. In D, it's the same amount of flux lines passing through as B, but they're going in the opposite direction in relation to the normal to the coil. So we can think of this as the maximum negative flux. So it'll be a maximum and it'll be down here somewhere. Let's say it's about there. And finally, as we come back to our starting position, the flux again is 0. Now, it doesn't take a lot of imagination to see that what we've got here is a pretty reasonable approximation to a sine graph. Now, please excuse my terrible drawing, but it's the best I can do. So there's our sine graph. So as the coil rotates, this is showing us what the flux through the coil is doing. And of course, this is just one rotation. If it keeps on rotating, the graph will just go on and on and on and on. So that represents one complete rotation of the coil. Okay, so let's now look at the gradient of this graph, the gradient of our flux graph, the purple graph. Let's see what the gradient is doing. So I'm going to get my ruler to help me here. So if we look at it, get our ruler up, and if we check out position, oh my God, it's a pretty inaccurate graph, but position B, actually the gradient should be, it's not exactly according to this graph, but it should be, change my colour, the gradient should be 0. So at that position B, the gradient of the graph, which is this second graph, should be 0. So around here, the gradient should be 0. So I'm going to mark 0 there. I'll try that again. Okay, so that should be 0. Because our gradient is 0. Where else is the gradient 0? Well, the gradient is 0 also here at position D. And please, once again, excuse my inaccurate graph, but that should be a gradient of 0. So the gradient is 0 there as well. If we have a look at position A, well, the gradient is large and positive. So our gradient should be up here, large and positive. On the other hand, if we look at position C, the gradient is equally large, but it's sloping in the negative direction. So it's large and negative. So we'll draw that about there. And moving on to the final point, point E, well, that's like point A. So point E and point A should have the same gradient, and so it should be just like point A, which is large and positive. So it should be about there. So if we now complete this graph, that's also sinusoidal in nature. And this is looking like a cos graph, isn't it? Not that that's important, but we're going to put all this together now to come up with our EMF. Now remember, the EMF, and this is where it all comes together, the EMF is the graph of the EMF is equal to the negative of the graph of the gradient of the flux graph. Well, here's our flux graph. This first graph is the graph of our flux with respect to time. With respect to time. The second graph is the gradient of our flux graph with respect to time. So this second graph was the gradient of our flux graph. The third graph, which should be the negative of the gradient of the flux graph, that will be the EMF. So the EMF, this last graph, will be the negative of this graph. It's the negative of the gradient of the flux graph. So how do we make this graph negative? Well, we simply, wherever it's positive, it goes negative, and wherever it's negative, it goes positive. So the gradient of this graph will look like this. When it's positive, it goes negative. If it's 0, it will stay 0. And where it's negative, it's gone positive. So there is a graph of what our EMF is doing as it rotates in the magnetic field. And one really, really important and I think interesting thing to note is this. The EMF is at its maximum. Here's the maximum EMF here and also at the corresponding point down there. The voltage is at its greatest when the flux through the coil is 0. When the flux through the coil is 0. When the flux through the coil is 0. So in other words, if you have a coil spinning in a magnetic field around and around and around, the point where the EMF or the voltage is at its maximum is the instant when the flux through the coil is in fact 0. And that's because that point corresponds to when the rate of change of flux is at its maximum. Now this really rams home the point that the EMF we're generating has nothing to do with the value of the flux through the coil, it's how quickly the flux is changing. And that is what is really, really important to pick up from this idea. So the EMF is determined by how quickly the flux changes. Okay, that concludes this lesson on flux and EMF graphs.